All right, so welcome to week 7, right? We're in the back half, heading on home here. Welcome to week 7 here in Math 202. And today we're going to wrap up our discussion of the change of transformations or change of variables. So if we do a transformation, we saw how we could build the Jacobian using the matrix. I'm going to show you a little bit of a trick for those where we don't actually have them as y equals and x equals, kind of like the example we saw at the very end of last time where we were doing that like transformation from a diamond into a square. But that's where we're going. And it dawned on me earlier today that I had forgotten to change the due date on the homework for this section, as I promised I would do. So you'll see that still says due tonight. It is not due tonight. I will move to next week. At least I don't think I did change it, or maybe I did. I don't know. That's
no, I think it's still.
Yeah, every day's a blur anyway. But I will definitely take care of that. So anyway, so with that, is there anything you guys want to chat about before we dive into continuing that? Any questions on anything?
Are we still having exam 2 on Friday?
We are still going to have exam 2 on Friday. We'll talk a little bit more about what that's going to cover and everything in a minute, but
Okay.
that is definitely still on tap.
Can we do question 8? 11 on the homework.
Which section homework, Jordan?
5.7.
All right. So number 8 on 5.7.
11.
11. Sorry. All right. Excuse me. We could definitely do that. I'll go ahead and pull that up. So Ralph also asked for number 9 in that same section, so we can definitely take a peek at those. All right, so let me go ahead and share my screen with you guys, and we'll get that going here. All right, so hopefully you guys see the assignment list here. Excuse me, got a little bit of a cough going. So let's take a look at 5.7. All right, so let's take a look here first at number 9. Okay, so this one says, in order to find the area in an ellipse, we may make use of the idea of transformations and our knowledge of the area of a circle. So for example, consider R being the region bounded by this ellipse. So hopefully you recognize that's an ellipse. It's centered at x equals 2, y equals 5. And then it goes left and right a distance of 7 and up and down a distance of 3, right? So it says the easiest transformation to choose makes u equal and v equal what? Okay, well, let's think about what we're trying to do. We want to turn this into a circle equation. And the easiest circle equation is going to be u squared plus v squared equals 1. Why would that one be super easy? Why might I want?
It's just a unit circle.
Yeah, it's just a unit circle centered at the origin. We know everything about it. So let's think about what kind of transformation we need to do to make it so that this will look like u squared plus v squared equals 1. All right, so let me just write this down real quick. And we'll go to the whiteboard. All right, so what we've got, this is our ellipse. But like I said, what I'd really like to have is u squared plus v squared equals 1. So what would that make us want to make u equal?
X minus 2 squared over 49.
Okay, so we'd want u squared to equal that. So what would that make u?
Plus or minus the square root of that.
Okay, so plus or minus, so we'll just go plus since it doesn't really matter. So the square root of it's going to be x minus 2 over 7. Does that seem like that'll work out for us? You square that, you get this piece, and we're where we want to be. All right, so then what should v equal?
Y minus 5 over 3.
Beauty. Okay, so if we go with these transformations, this thing just becomes u squared plus v squared equals 1. So if we are going to like find the area or whatever, we could just do it in polar and we're good to go. Okay, so this is what I'm going to let my u and my v equal. And then you may have noticed for the second part of that equation or question, it said, then that would make x equal what and y equal what? So x is going to be 7u plus 2, and y is going to be 3v plus 5. And that's just solving these guys for x and y. So these are really the transformations I'm doing. And you can see if you were to take that and plug it in, right? Like take this 7u plus 2, fire it in there. 7u plus 2 minus 2 is 7u. 7u squared is 49u squared. The 49's cancel and we're left with u squared. And then similarly, you can see the same thing happens with the y. All right, so far so good?
Yeah.
Yeah, we're doing all right. So let me go back to the question just so that we can kind of keep track of what we're doing here. And they're really just trying to walk us through the process. So we just chose a good change of variables. So we got our u and v equals, we got our x and y equals, but now we want to find the Jacobian. Right? We want to find the Jacobian because then we know what the original area will be. It'll be just the integral of this new thing over where the region is the circle. All right, so let's get the Jacobian. So let me go back. So here we are. So how do we get the Jacobian? Do you guys remember?
We need the derivatives of I'm trying to think of what we need respect to.
Okay, so we're going to make a 2x2 matrix and we're going to find its determinant. All right, so Victor just put into the chat box dx du, dy du, dx dv, and dy dv. So yes, we need all of those. So we're going to have dx du, dy du, dx dv, dy dv. And like I mentioned before, you could instead go down the column dx du, dy du, and then the other column be dx dv, dy dv. Either way, you'll get the same determinant.
So just as long as there's something in common with each row or
Each
column.
row and each column. Yep.
Got
And as long as you're consistent. Okay, so let's put these in. So dx du, well, dx du is 7. dy du is 0. There are no u's in that. dx dv also 0. dy dv is 3. So the determinant of this is 21. So if we go back to the original, right, the area of this thing, so R is the is that elliptical region, and then the dA is either dx dy or dy dx, whichever. But we've just translated that now so that we're integrating over the circle, and it's going to be 21 times du dv or dv du, whichever way you want to do it. I'm just going to write it as du dv. So before we deal with trying to do that integral, how are we feeling about finding that Jacobian?
Pretty good.
Good.
We good? Thumbs up. All right. So now it's just a matter of doing this. Well, that 21's a constant, so we can pull that out. So we now have to integrate over the circle, du dv. Well, I'm not going to bother doing the integral because I know what I'm going to get here since I'm integrating 1 is just the area. And so what's the area of the circle in the UV plane?
Wouldn't it just be pi?
It would just be pi because it's a unit circle. And the unit circle has a radius of 1. So there's the area of that ellipse.
I always wondered how you found the area of an ellipse, and this is how you do it.
This is one way. I mean, there are lots of ways. You can actually use second quarter calc to do this. You know what I mean? Like take this equation that we started with and solve it for y. You get your plus or minus. The plus is on top, the minus on the bottom. Do your integral, top minus bottom, whatever. That'll get you it as well. But check this out. Let's make this generic. Let's just make this really, really generic. Actually, before I go there, we all good? You kind of see how we got 21 pi?
Yeah.
Okay, so let's make this super generic. I'm not going to clear. Oh shit! I was going to. I'm not going to clear everything. Hold on. There it is. All right. I meant to erase. So here's what I'm going to do. Let's make this generic. So we'll have good old x minus h squared over a squared plus y minus k squared over b squared equals 1. So I'm not specifying the center, and I'm not specifying the sizes. But I still want to make it look like u squared plus v squared equals 1. All right, so let's see if we can use what we did here to figure out what our new u would have to equal. So what are we going to want u to equal in this case?
X minus h over a.
Cool. X minus h over a. And then v. Same kind of trick, right? We'll make it y minus k over b. So if we allow u and v to be these two things, one squared, they become u squared plus v squared. All right, so then we need to solve those for x and y. So we've got x is equal to AU plus H, and y is equal to BV plus K. Right, notice how it's following the pattern. But now let's set up our Jacobian. So our Jacobian is going to be dx du, so A, dy du, 0, dx dv, 0, dy dv, b. So that's going to be A times b. So then our area is going to be AB times this integral over the circle. And we already know that the unit circle is area pi. And check it out. There's the formula for the area of any ellipse.
Nice.
Right? Power, man. Are you kidding me? This is awesome. So all you got to do to get the equation or the area of an ellipse is just multiply the two the semi-major axis and the semi-minor axis. Multiply those together times pi. And you can see that the circle is a specific case of this, since the circle is an ellipse, right? The circle is such that the major and minor axes are both the same length. The halves of those are both r. So you get pi times r, which is your good old pi r squared. So there you go. You now have developed the area formula for an ellipse.
And that's any ellipse. Yeah.
Any ellipse. I don't care where it's centered. I don't care what A and B are, because we did it generically, right? We were thinking like mathematicians. Instead of doing it over and over and over and over, do it once. See what spills out. So you could do the similar, like you could do a similar trick for like any kind of shape, right? If you want to find the formula for the area of a rhombus, if you can figure out the translations that turn it back into a square, then the Jacobian of that transformation is just going to be the multiplier on the area of your square, right? Or insert favorite thing here. And in fact, when you go to 3 dimensions, and we'll talk about 3 dimensions in a little bit, this then could extend to the same thing. Like you want to find the volume of an ellipsoid. Well, do a transformation to bring you back to a sphere, specifically the unit sphere. And then you can get that. So we'll actually do that. Remind me, and we'll do that as an example when we get to 3D of finding the generic volume formula for an ellipsoid. Anyway, so okay for that one?
Yes.
Yeah, I have a quick question though.
Sure, go for it, Bradley.
Would you be able to find the area of an ellipse if you knew how far you were from a focus and you didn't know the center?
So if you just knew a point on the ellipse, basically,
Yeah.
if you just know one point, and you know where a focus is,
Yeah.
let's see, would that be enough? No, that would not be enough,
I figured.
because there's more than one ellipse that could do that. Let me just clear this real quick. Because so here's a focus, right? And then we've got some other point. The problem is there are an infinite number of ellipses that will do this, right? Like this could be on an ellipse that looks like that. It could also be on an ellipse that does, well, okay, it went through that point. Never mind my drawing, but I think you understand what I'm saying.
Yeah, I
right?
get what you're getting at.
Is that there's a ton. Now, if you know both foci, okay, so we got focus 1 and focus 2. So if you knew both of them, and then you knew some random point that was on the ellipse, now I think you are guaranteed I think, because let's see, if you know that, you know the middle, so you know your H and K, the C gives you a relationship between A and B, this gives you another, yeah. So this would be enough for you to now find the ellipse.
The reason why I asked is because now that I know the area formula for any ellipse, I was like, I want to know what the area is of the orbit of the Earth. But then I thought to myself, I don't know what the center is.
Okay, so the Earth, though, we do know the perihelion and aphelion, the closest and furthest approaches to the sun. So
Okay.
if you wanted to figure that out, here's how you could do that. So here's the sun, right? And then the Earth, we do know closest point, and we also know furthest point. So I'm going to exaggerate it so you can definitely tell that there's a longer and a shorter. Our orbit is pretty circular, so they're not that different. But this is something that would be like a really easy Google search, right? Just be like, what is aphelion? What is perihelion distances? And you'll get them. And so in essence, what you're going to know, like if you know those two numbers, let's just call them X and Y, then you know that 2A is equal to X plus Y. So you can get your A, right? You just average the aphelion and perihelion. And that gives you your A. And then because you know A, you can then figure out where the center is.
Okay.
Right? Because A is, so let's just say that this is the center. Because those are each then A. So you know where the center is, which you can also find C, because C is the distance from the center to the focus. And we know that C plus X is equal to A. So we got A leads us to C, and then we know that the relationship between A, B, and C in an ellipse is given by this. So you can get B then from that. And you've got the entirety, because you can make your center be just 0, 0, because it doesn't really matter. Plus, as we saw, the only thing that matters in terms of finding the area is A and B.
That's tight.
So if we really wanted to, we could probably just figure out what B is in terms of X and Y, just like we did with A, and then multiply them together, and that would get us the area of the Earth's elliptical orbit. But that's more algebra than I want to do right now.
Well, thank you.
Yeah, you're welcome. So you could actually do this with anything if you knew closest approach and furthest approach. You know, so like Halley's Comet, same story. Jupiter, same story. You could do it for the moon around the Earth, because we also have, those are called apogee and perigee. Right, look at the roots there. So helios is sun, geo, Earth. So apogee, perigee are the same thing for the moon going around the Earth as aphelion and perihelion are for the Earth going around the sun. So same argument, same picture, just different scale. Anyway, cool.
Yeah.
Cool. And I will say this is one of the things that I love about teaching this class in specifically is that by the time you get to vector calculus, you guys have seen so much math and seen so much science that you really start seeing the connections and where we can use this stuff. And I love that because it's no longer a, well, why are we doing this? Right? I rarely have to answer that question with you guys because you immediately start seeing where you can use it. You know, so anyway. So we good for this one? I think this was number 9, maybe. I don't know. But we'll go look at the other one. Let me bounce back over there. So here's our homework list. The other one was number 11. Was that correct, Jordan?
Yes.
Yep. Okay. All right. So let D be an ellipse rotated counterclockwise by pi over 6 radians as pictured below. Before rotation, the horizontal axis was 3 and the vertical axis was 4. All right, so it says convert this thing into an integral over a polar into an integral over a this is really weird wording, but over a polar integral over a unit circle. Okay, so basically they're saying convert this so your transformation is you're on a unit circle. All right, so and you'll even see the bounds, right? The bounds 0 to 1 and 0 to 2 pi. Those are your r's and your thetas for a unit circle. So let's kind of do a similar thing in terms of setting up this integral. All right. Let me write down the pertinent information here again. So we had 3 and 4, and we're going pi over 6 counterclockwise. Okay. So I'm going to go back to so let me clear this picture. But maybe let's start here. Let's start with it not being rotated. So we'll go back to what they told us about this ellipse before rotation. Right, before rotation, they said that it was, and I think I remembered which one was which, but it was, I think horizontally was 3 and vertically was 4. So the way that we had been describing things, A is 3 and B is 4. So can you give me the transformation for these? How about this? How about this? We'll even, let me give you the equation of this ellipse before it gets rotated. What would we do as our transformation?
Same thing we did last time.
Okay, so what would U equal?
X over 3.
Cool. And V?
Y over 4.
Cool. All right, so for this one, it's easy enough. And I mean, we're basically there, right? We would just go, okay, X is equal to 3U, Y is equal to 4V, and so on and so forth. So without that extra rotation, this is exactly like that other problem, right? In fact, you should be able to tell me what the Jacobian is. What's the
12.
Jacobian here? Yeah, it's just 12. Okay. Cool. But what about the rotation? Because this is all well and good, but what we really want is, I'm going to exaggerate it a bit, but we want that, right? Where we've rotated pi over 6. All right, well, how do you think we're going to rotate pi over 6?
Convert it to polar. Throw in pi over 6 into our cosine and sine.
Okay, I definitely like that kind of idea, because if we were, let's go back to just polar. I don't even know what I'm trying to do down here. Jesus. It's the COVID. I'm telling you, it's the COVID. I probably shouldn't make jokes like that just in case it really is the COVID. All right. So let's think about taking a point here that's r theta. And I want to rotate it. What would be the corresponding coordinates now?
Theta plus pi over 6.
Yeah, because we're going pi over 6 counterclockwise. So if we were going to look at x's and y's, x normally would be r cosine theta and r sine theta, right? So this is with no rotation. But then if we went over to rotation, what would it be?
X or r cosine theta plus pi over 6.
Okay, so we still have that pi over 6. So we're going to have our r times cosine, but now instead of just theta, we have to account for that pi over 6. And the same thing here, right? So basically what we're trying to do is equate those x's and y's. But here's what's probably going to trip you a bit. These guys have to be minus pi over 6.
Why?
Good question. That's what I was going to ask you guys. Turns out it's not an identity, Victor. It does have everything to do with counterclockwise, Ralph. But counterclockwise normally means add, right? Like I had in my picture. Think about this. Oh, sorry, go for it. Who is that?
I was going to say the only thing I can think of is like when you look at an ellipse or a circle that's not centered at the origin, it's minus that value. That's the only rationale I can think of. It's just because.
Just because. Okay, well, it's definitely along those lines. Like think about horizontal transformations, right? When you wanted to shift right, what did you do?
Subtracted.
You subtracted. And when you moved left, you added. And so Ralph just put in here, oh, you're trying to make it back into normal. Yeah, that's kind of what we're doing. When you have those transformations, is you're kind of shifting it back to what it once was. Right. And so this is definitely trippy. But when you do transformations like that, when you do shifts, the shifts are opposite what you think. Even the vertical shifts, like we never did it this way, but you remember the good old like y equals f of x plus b, right? And this would say you're moving it up. Well, if we had really thought of it, it was y minus b. That was the transformation on y. And so even though it was an up, it was a subtract. It's always the opposite of what you're trying to do.
That
So,
makes sense.
yeah, so it's one of those, it feels wrong. But in the end, it's why do we do it this way? Because, but Ralph, I think, hit it when he said on the chat, oh, you're trying to bring it back to normal. You're trying to bring this point back to that one so that then we can transform it into the unit circle, right? Think of it as a series of two things. There's we're rotating it back and then converting to a circle. So with that said, now we've got our X and Y. We can now convert these things using these guys. So somebody was just saying something and I talked over him. No, we're all right. So this is just a matter of putting two transformations together. There's the transforming it into a circle, and then there's the rotating it appropriately. So you can think about it in two ways, but I would go ahead and just put that rotation in here for your X and your Y. So you get your U's and V's in terms of R's and thetas. And now we haven't talked about this, but I will just tell you that if you have two transformations, because like what we're doing here, let me find some space to write. What we're really doing here, right, is we've got the XY is going to UV, which is going to R theta. And so each of these is going to give us a Jacobian. So I'll call it Jacobian 1 takes us from XY to UV. Jacobian 2 takes us from UV to R theta. If you want to do the entire jump, the Jacobian is just the product of the individual Jacobians. So what we can do is we can look at what's the Jacobian from XY to UV. And then in these X's and Y's, those are now U's and V's. Does that make sense? Right, because the U and V were those were the guys that were bringing us to the circle. So then we have to rotate that guy. So basically you can take your integral and turn it from XY's into UV's, and then from UV's into R thetas. Anyway, so does that make a little more sense with this one? Kind of the process here when you've got more than one transformation.
So once we get U equaling and V equaling, do we convert that into just to R's as well? They can have them as R equals.
Okay, so so for these, you're actually ready to go.
Okay.
Like for this one, if we're going to try to find that Jacobian, du dr, du d theta, dv dr, dv d theta, right? We already have those things. So I guess this would be, according to the way I've written it, this would be J2. But just find that determinant. just like up here, J1, dx du, dy du, dx dv, dy dv. And again, we already have those. This one's easy, it's 12. This one, not quite as easy. But it's not actually bad because you can use the Pythagorean identities. So, well, fine. That's still equal to R. The minus pi over 6 doesn't do anything with your derivatives. And you still end up getting sine squares and cosine squares of this thing. So that just ends up being R. So it doesn't matter in terms of the Jacobian, but it definitely does matter when it comes time to converting. If I remember correctly, we were integrating 8x plus 2y. So you're going to turn that into u's and v's. So that would be 24u plus 8v with Jacobian and stuff, right? And then you'd have to use those to convert your u's and v's. So what we're going to end up integrating will have that pi over 6 in it. And so will matter, but it doesn't affect the Jacobians at all. All right, so it's at this point, I'm going to ask, what questions do you still have? Because I know you still have questions about this. So what more can we talk about here?
Was that 8x plus 2y just random?
That was what I was told to integrate. If you go back and you look at my problem,
Oh, okay. Okay.
that was the function I was integrating. So yours
Got
could
it.
be completely different. But yeah, that was the function I'm integrating.
Got it.
If this had just been a find the area kind of question, the rotation doesn't matter whatsoever, right? It would have still just given me the same area. But since I'm integrating just a function of x and y, then I do have to account for that rotation because those are now different x's and y's. What other questions can I help answer?
Is J2 always R?
Oh, no. This one's just R because it's polar. It's the conversion into polar, and we've already seen that Jacobian is R. I just know that's what I'm going to get if I do the Jacobian on these guys. Just like J1's not always 12, but it is when we're converting this ellipse down into a circle.
Also, where did you get the 24 from?
Remember down here I had 8x.
Yeah.
X is 3u. So I just substituted that in, 8 times 3u.
Okay.
And similarly, that's where that 8 came from. It was the 2 times the 4 and the y.
All right.
So obviously, if you have a different ellipse, you're going to have a different set of transformations. If you have a different rotation, that's going to get affected in here. If you have a different function that you're integrating, that's going to get affected as well. But do them in the multiple steps, and you'll be good. All right, so how are we feeling about that now? Decent?
Pretty good.
Cool. All right. Well, then I'm going to go ahead and stop sharing this one. And I'm pretty sure that was all of the homework questions you guys asked about, right? Yep, just 9 and 11. So again, those aren't actually due tonight, right? 5.7 is going to be due next week, but it's totally cool that we talk about it now because it actually is going to lead into a few things that we still need to talk about with these transformations. I want to share specifically two things today. One, I want to share how we do this with three-dimensional transformations, right? Because so far we've only been in 2D world, and we need to allow ourselves three dimensions like cylindrical and spherical. And in fact, I'll show you then where that spherical rho squared sine phi shows up. So I want to show three dimensions, and I also want to show you a trick that doesn't make it so that you actually have to solve for x and y, because that's not always easy to do. Sometimes it's a little bit more challenging. And in fact, I want to revisit the example we ended with last time to show you this kind of trick. So give me 1 second. I'm going to hop up to the whiteboard and I'll be right back with you. All right. Let me get rid of, oh, you guys remember this stuff, right? Related rates. They hate it.
Your class?
Yeah, so for first year calc, we're doing related rates earlier this morning. They're not a huge fan. But you guys remember the hell that related rates is, so.
Yeah, it was painful.
Not as bad as power series.
Yeah,
Yeah,
isn't
that's
it
true.
how
It wasn't as bad as series.
calculus does this, right? Like you're going along, epsilon delta, oh Jesus. Related rates, oh my God. Probably trig sub, the next one. And then power series, right?
Yeah.
So it is funny how it just kind of goes through its waves, but I don't think there are any big spikes in this class at least. Anyway, I digress. So we're still working on these transformations. And let me just remind you the example that we did last time. We were looking at changing a region that was the diamond shape here. And we saw that a really good way to change this was to look at the equations here of these different lines. So like this one was y equals x. This one was y equals x minus 2. This one was y equals negative x, and this was y equals negative x plus 2. And what we did was we basically just rewrote those equations so that we had x minus y equals 0. So that was this top one. The parallel line to it was x minus y equals 2. And then the other ones were x plus y equals 0 and x plus y equals 2, right? So those were the four boundaries. And we saw that a really good transformation for this was to let u equal x minus y and for v to equal x plus y. So none of this is new. If you go back and you look at your notes from Friday, we went through, I forget what we were integrating. We were integrating like x minus y squared or something, but I don't really care about that. I want to talk about finding the Jacobian. Because do you remember what we had to do next in order to find the Jacobian? And he takes the silence as, nope, don't have an idea of what we did. We had to get these as x equals and y equals. Because when we do the Jacobian, remember how that's formed? It's the partial of x with respect to u, y with respect to u, x with respect to v, and y with respect to v. So we need to have those things as x equals whatever and y equals. And that was a little challenging. And to remind you what we did, we actually solved this system,
Yeah.
right? Like we added them together. So that gave us u plus v was equal to 2x. So x was equal to 1/2 u plus v. And then when we subtracted, if we took like v minus u, that gave us 2y. So y was equal to 1/2 v minus u. So there was a bit of work to get there, right? We had to convert these guys into the x equals and y equals so that we could then create our Jacobian, right? And so what we actually found in this case was that Jacobian, it was 1/2, let's see, minus 1/2, 1/2, 1/2, which is 1/4 plus 1/4, which is 1/2. So for this one, we found the Jacobian 1/2, no big deal. And I say no big deal, but it was a little bit of a big deal because there was work to get to the x equals and y equals. And these were nice, right? I think you can objectively look at these transformations and go, yeah, those are nice transformations. We don't have, u equals natural log of xy over x plus y, or anything like that, which would lead to kind of gnarly substitution trying to solve. Okay, so let me just give you a little bit of a tip. If you're looking at going from, say, xy to uv, and let's just call this guy J for our Jacobian. Obviously, if we go the other direction, so say we're going from uv back to xy, there's also going to be a Jacobian, right? I mean, if we're going to go backwards on this, transformation, and we're already talking about one-to-one transformation, so that we know that there is going to be an inverse. There's going to be a Jacobian value there. So the question is, what is that Jacobian? Well, do you have a guess?
The reciprocal?
So 1 over?
Yeah.
Seems like a pretty obvious kind of choice, right? Which of course is dangerous, right? Because as soon as you go, oh, it must be, that's when it turns out that it's not, right? And then you're like, God damn it. But it is. It is exactly the reciprocal. It's 1 over j. And to see why that is, go back to something I just mentioned a little bit ago with the example we were doing with the two transformations in order. And remember how I told you what you can do is you can take those Jacobians and multiply them together. So think about this. Suppose we were going to start at xy, go to uv, and then go from uv back to xy.
1.
Okay. The product of those has to equal 1. Because the Jacobian going from xy to xy, well, we didn't change anything, so it must be 1. So j times whatever this is has to equal 1. Therefore, it must be the reciprocal. Okay, so if you were to do the inverse transformation, you just get the reciprocal for its Jacobian. So for all of those, like remember when we went from rectangular to polar, we got a Jacobian of r. If you're going to go from polar to rectangular, you're going to get a Jacobian of 1 over r. Go to 3 dimensions, because this should still apply to 3D, right? So when we went from rectangular to spherical, we saw, well, you were told that the Jacobian was rho squared sine phi. Going from spherical back to rectangular, the Jacobian is 1 over rho squared sine phi. Okay, so should make sense. All it is the reciprocal. Now, why I even bother mentioning that is, check this out. Instead of going through this whole process of trying to solve it for x, y, and all that, let me show you the reciprocal Jacobian. So this is going to be the Jacobian from uv to xy. Okay. In terms of what it's going to look like, well, it's going to be du dx, dv dx, du dy, dv dy. So it's the exact same idea, except we're doing u's and v's. And watch what that ends up being in this case. So if we just went with this is what u equals, and this is what v equals, du dx is 1. dv dx is 1. du dy minus 1. dv dy 1. Well, that Jacobian is 2. We take its reciprocal, it's 1/2. And by going that direction, we skip over having to do all of the solving for x and y. So remember this, and use it when you've got just u equals and v equals. You don't have to go to that next step of solving for x and y. Go back and look at that example with the ellipse. So this may not be exactly the ellipse that we were doing in that homework problem, but I think at least this is the one from the transformation, or that had multiple transformations. But let's look at this guy. Now, you already know the answer to what is the Jacobian if we go to the unit circle?
12.
12. We already know it's 12. But let me show you how we could get there even if we don't solve for x and y and go through the process. So we know that we would want u to equal x over 3. And we want y, or sorry, not y, v to equal y over 4. All right, well, let's find this Jacobian. So du dx, dv dx, du dy, dv dy. Okay, so du dx is 1/3, dv dx is 0, du dy 0, dv dy 1/4. That determinant is 1/12. So the Jacobian from xy to uv is the reciprocal of that. 12. All right, so this is going to be a huge time saver for you, huge time saver. If it's not really clear how to get these things as x equals and y equals. Now, I would never do it with this one. This one's easy. X is equal to 3u, y is equal to 4v, go. But you can see how in certain circumstances, yeah, I don't want any part of it. All right, so let me show you another one where this can be kind of handy. Before I do that, questions? We feeling okay about this? Maybe are we at least feeling we can do it? Maybe not
Yeah.
100% on board with why and all that.
Yeah.
Okay. So this one, I don't remember if this was on an exam or a homework, but we definitely saw, geez, it might not even be you guys. No, it has to be you guys because first year hasn't seen this yet, I don't think. Well, anyway, so let's say that this is our region that we're going to integrate over. All right, so it's going to be trapped between 1 over x, 4 over x. This is y equals 1 over x. This is y equals 4 over x. And then we're going to go with y equal 1 and y equal 4. This was you guys, right? Exam question, I think, maybe. Regardless. Let's say that this is R. Now, you can do this without any problem. And in fact, if you're going to do integration man, probably easiest to have integration man be sideways, right? Oh, this was definitely you guys. Now I remember. Hopefully you guys can remember.
It was definitely us.
But check this out. We can do this with a transformation. Let's think about what those 4 sides are. So the 2 black ones are easy. They're just y equals 1 and y equals 4. The others, y equal 1 over x, well, let me rewrite that as xy equals 1. The other side, y equals 4 over x, I can write that as xy equals 4. So here's what I want. Instead of xy, I really want that to be, say, u. So I'm going to let u equal xy. Because then these boundaries become u equal 1 and u equal 4. Way easier. Well, these guys already are just 1 and 4. I like that. I just can't use y anymore. So how about I just change that name to, say, v. So if I do these transformations, this is going to make it so that my v's are between 1 and 4. And my u's are also between 1 and 4. And so my integral is going to be much easier. So I don't remember what our exam question was, like what we were integrating. I'm just going to say we're finding the area, all right? So we were originally doing this. Well, now we're going to be integrating from 1 to 4 and 1 to 4. Let's put a du dv. But now the question is, what am I integrating? Well, let's find the Jacobian. All right, so instead of bothering to solve it for y equals and x equals, let's use that little inverse trick. Okay, so I'll do that up here. Let's look at du dx, du dy, dv dx, dv dy. Let's see what that's going to look like. All right, so du dx, that's just y. Du dy is x. dv dx is 0. dv dy is 1. So that's just y. But I'm not going to put y here. What am I going to actually put?
1 over y.
1 over y. All right, but this is still a problem. What's the problem with 1 over y?
Well, it's a variable.
It is a variable.
And we're integrating with respect to u and v.
Okay, so it is in terms of u and v. So what I need to do is replace that. So I need y in terms of u and v, and Victor just threw it into the chat. Y is equal to v. Right here. Right? Y is equal to v. So this thing became the integral from 1 to 4, integral from 1 to 4 of 1 over v du dv. So whatever that was originally, whatever the integral was originally, it now just looks like this. And watch how fast this is now. Integrate with respect to u. Well, there is no u. So the 1 over v just gives us 1 over v. The u, du gives us a u from 4 to 1, that's 3. Okay, well, the 3 over v gives us a 3 natural log of v, evaluated at 1 and 4, which is 3 natural logs of 4. Done. And even in this circumstance, I think it's faster to do this transformation than to set it up and do integration man and all that business. So even ones you've already done, there are many circumstances where doing this change of variables makes it a lot easier.
What would you have done if we busted this out on the exam?
I probably would have said something like, which online resource did you just use to help you do this question? Because we weren't there yet.
Didn't
Now,
even think about that.
now I'd probably be like, cool. Good job seeing that you can use a transformation and do this much faster. Right. But it's I don't know how many times we run into the same story, right? Where it's, all right, here's another way to do this thing we've already done. And like, is it a better way? Sometimes. Is it a faster way? Yeah, definitely sometimes. And a lot of it comes down to the rest of the problem, right? Which way do you want to do this? But these transformations definitely open up the possibility, especially when your boundaries, when the boundaries to your region have similarities, right? Like that's what we're seeing here. That these boundaries, now that I've erased them, but those boundaries are similar form. The two were hyperbolas. Hyperbolas are hyperbolas, but they're similar in structure. So if we can substitute in for that hyperbola, well, now we've got a rectangular region in this new world. And all you have to do to account for that is throw in a Jacobian. So when I first learned Jacobians, I wasn't a huge fan. As I started doing more math and I started seeing the power of Jacobians, I started becoming a big fan, like huge fan, because, oh shit, yeah, I'll do a little bit of work to turn my integral into something easy. Absolutely. Right. And also consider my age, right? I mean, I joke about being old. I know I'm not old, but I'm old enough that I didn't have the technology that you guys have. It wasn't, I could just type into my phone, like we even had phones back then. That's not true. There were cellular phones, but they were like the ones that were in the car, or watch something like Saved by the Bell, the big like block phones. And only like really rich people had them. So, but we didn't have that technology. I couldn't just type it in and have it spit out an integral. I had to do it all by hand. I was very willing to do a little bit of algebra to make my integral easy. Because algebra, whatever. I like algebra. So just take that also whenever I talk about how much I love something, realize that it's partly due to how I grew up. And in the math world, it was limited technology, right? We had calculators, but we didn't have graphing calculators. we were one step beyond the slide rule.
Summer integrals are just gross.
Yeah, sometimes they're gnarly, right? And you're like, oh, now I need to do trig sub, and then after I do the trig sub, there's an integration by parts, and ugh. When instead I can just go, oh, I'm integrating from 1 to 4. Sweet, that's easy. Anyway, all right. So remember this trick for you don't actually have to solve for x and y. Okay, you don't. You can just do it with the partials of u with respect to x and y, and then take the reciprocal. All right, so then what about 3D? What about this 3D business? Like, what if we want to extend this to 3 dimensions? How do we find the Jacobian? And so let's specifically look at the conversion from rectangular to spherical. All right, so this will be our 3D. But the specific example, let's look at x equals rho cosine theta times sine phi, y is rho sine theta sine phi, and z equals rho cosine phi. So those are the 3 transformations. So we're basically going from x, y, z to rho theta phi. And it should make total sense that even if this is 3-dimensional, we still need to have some sort of a Jacobian times, in this case, it's going to be d rho, d theta, d phi, right? But how do we figure out what this Jacobian is? Well, the good news is we don't have to learn anything new. It's still going to be the determinant of a matrix. This matrix is still going to hold the partial derivatives. But what is the difference?
3 by 3.
Yeah, it's 3 by 3. So if we're going to do the same thing in 3 dimensions, no big whoop. It's just now we're going to have dx dr, dy dr, except not r, how about rho? Because we're going to polar. So dx d rho, dy d rho, dz d rho. That'll be our first row of the column of the matrix. It could be the first column. The second row now is going to be dx d theta, dy d theta, dz d theta. And then the last row is going to be dx d phi, dy d phi, dz d phi. And so the argument for the 3-dimensional case is really the same as with the 2-dimensional case. You may remember in the 2-dimensional case, we were looking at the area of a parallelogram. Okay, well, in the 3D case, we're now looking for the volume of a parallelopiped is the name of it. But think about a box whose sides are all parallelograms. That's a fun word, parallelopiped. But we're looking for its volume. And I don't know if you remember this from when you learned about dot product and cross products and all that, but you can actually find the volume of a parallelopiped by doing what's called the triple scalar product. And this is a little bit of an aside, but helps you see where this is coming from. So let's say that these are the 3 vectors that form our box. So if I go to kind of making it look 3-dimensional, hold on, I can make this look 3D. So there's that parallelogram, and there's that parallel. Oh, I guess this one's looking mostly square, but all right, so you can kind of see our little parallelepiped. So these are 3 corners of that box. And they're not necessarily at right angles, okay? They can be at any order. But if these guys are U, V, and W, you actually get the volume by taking U dotted with V cross W. So it's called the triple scalar product. Because we're multiplying three vectors, so triple product. And it's called a scalar product because the result is scalar. You may remember that question I asked you guys on the exam about doing like R cross U cross V or whatever, or dotted U cross V. It's going to be a scalar, it's just going to be a number. But this is how you get the volume. And you actually find it by taking the components of those three vectors, putting them into a 3x3 matrix and taking the determinant. Okay, so just, you can trust me that that's true. That's how we do this. So then if you think about what we're trying to do, when we did the Jacobian in 2D, we were basically looking at the two vectors on the sides of the parallelogram, and we wrote them in terms of the partials. Well, now all three of these vectors are going to be in terms of the partials of their corresponding chunks. And that's where you get this form. So it's exactly the same argument, just bumped up to volume of the shape instead of area of another shape. So, all right, but let's actually play this out with going into spherical. And what you're going to see is that we get rho squared sine phi. All right, so let's set this guy up. Let's get all these different quantities and put them into our matrix. So dx d rho is going to be cosine theta sine phi. dy d rho, sine theta sine phi. And dz d rho is cosine phi. So there's the first row of this matrix. All right, now let's go to thetas. We're going to get a minus rho sine theta sine phi, a plus rho cosine theta sine phi, and then a 0, because there are no thetas here. And then when we go to the phis, we get rho cosine theta cosine phi, rho sine theta sine phi, and then minus rho cosine phi. Or sorry, this was a cosine, this minus rho sine. All right, so now it's a matter of finding that determinant. So I'm gonna start writing over here because we're gonna get, it's really big. So if we go down in the positive directions, I'm gonna get a minus rho squared cosine squared theta sine cubed phi. So that was those three being multiplied together. The next piece I'm going to get is a plus 0 sine theta sine phi times 0. Sweet, that's 0. The next piece, I'm going to get minus rho squared sine squared theta sine phi cosine squared phi. So that was those three pieces. All right, so now we do the three backwards and subtract them. So then we're going to get a minus rho squared cosine squared theta sine phi cosine squared phi then we're going to get a minus rho squared sine squared theta sine cubed phi. And then we're going to get minus 0. Okay, so there's the determinant. There's the Jacobian. And I know you're probably thinking, you're looking at that going, that does not look like rho squared sine phi in any stretch of the imagination. Well,
They all have a rho squared in common.
oh, okay, they do all have a rho squared in common, so we're going to make use of that. You want to just pull all that out right now? Let's just, okay, let's do that. In fact, it's all a minus rho squared, so let's just pull all that out. So we have minus rho squared. We got cosine squared theta sine cubed phi plus sine squared theta. Oh, actually, you know what? Hold on. Let's do one more thing. They all have rho squareds, and they all have a sine of phi. Let's pull that out too. So we get cosine squared theta sine squared phi. This one we're going to get sine squared theta cosine squared phi. This one's going to give us cosine squared theta cosine squared phi. And then the other one gives us sine squared theta sine squared phi. All right, so that was just simple factoring out, no big deal. Now let's use some trig fun. Check out these two.
One.
It's going to be 1 cosine squared phi. Right? If I factor out the cosine squared phi, I have sine squared plus cosine squared, which is 1. So that just becomes cosine squared phi. By a similar argument, these two, if I factor out a sine squared phi, I'm going to get cosine squared theta plus sine squared theta times sine squared phi. So that's just sine squared phi. All right, well, I'm adding those together. Cosine squared phi plus sine squared phi.
1.
Does that also equal 1?
That's also equal to 1. So once all that's done, all of that simplifies down to just a minus rho squared sine phi. Okay. So the only thing left that we have to worry about is that minus sign. I mean, you see the rho squared sine phi. It's jumping out at you. Okay, so why does this end up being a plus? Well, it turns out that the Jacobian itself is the absolute value of this quantity. It's always a positive, because if you think about areas, go to areas, positives go to positive. So we always take the absolute values of these. So absolute value, boom, there's your rho squared sine phi. So that's how we knew, or that's how I knew back when I told you, this is what you have to put in. You can also see it geometrically, right? Just like we were able to do it for like polar geometrically, you can do it with this as well. It's just, it's a lot faster using Jacobians. I also like this one just because it involves a lot of trig. And I love this. I love when you get something big and gnarly like that just simplifies, goes away. Yeah, it's just one. All right, so the moral of the story here is that you go to 3 dimensions, nothing changes. You still create the matrix. It still houses all these partials, right? And there you go.
So what I'm a little confused on, when you do your determinant of 3 by 3, how do you get the minus? Is it backwards? Like, do we go diagonally initially, and then do we do it backwards again?
Yeah, and then you go this direction. And all those in the red direction get a minus, which is where all those were coming from.
Got it.
The other ones were negative just because of the fact like this had a negative rho sine phi in it.
Yeah.
And then the other reason like that we just take the absolute value is you probably have not learned this because you'll learn this next quarter. So little spoiler alert. When Larry gets to it, pretend like you never heard it before, okay? Yeah. When you find the determinant of a matrix, if you swap 2 rows, all you do is you change the sign of the determinant. And think about what that would mean here if I were to swap 2 rows. All that means is I'm doing them in a different order. So instead of saying going rho theta phi, I'm going rho phi theta. Does that change my transformation?
No.
No, it doesn't change my transformation. It's changing how I decided to order things. Just like we don't necessarily have to write X, Y, Z. We could do X, Z, Y, right? We don't because there's kind of a standard. But when it's coming to a transformation, well, you can transform however you want. So there shouldn't be any difference if I do say rho phi theta versus rho theta phi. The absolute values take care of that. So that's the other reason why we always take absolute values of these Jacobians, because all we had to do is switch the order and then it's still the same transformation, just our Jacobian changed signs. All right, other questions on this guy? All right, if you wanted to, feel free to kind of do this with your conversion to cylindrical. X equals r cosine theta, y equals r sine theta, z equals z. And you can set up the matrix and do the determinants, and you'll see that you end up getting, again, just r. Excuse me, it plays out. So it's kind of nice that even in 3D it works out. Well, it looks like we're pretty much out of time. As always, time just sort of seems to escape us. But as they say, right, time flies when you're having fun, and we're doing some kind of cool stuff now. So just some things to remember. First of all, homework, there's the one section due tonight. I'm bumping the other one forward. I think I'm actually going to skip, just entirely skip this section on centroids, moments of inertia, and all that. I'm not 100% sure. I want to look into it, make sure there's nothing in there that I think we really need to talk about, because we're kind of falling a little bit behind on our schedule. I'm not terribly concerned, but we definitely need to move on into chapter, whatever our next chapter is, 4 or 5, or whatever, because this is where I start getting interesting, start getting to do some cool stuff with other kinds of integrals. Like I'm going to introduce you to line integrals and surface integrals and stuff like that. So I think I might jump ahead and just skip that section entirely. The other thing I want to remind you is we do have an exam on Friday. That is still the plan. In terms of what it's going to cover, I think it's going to cover up to and including this stuff on Jacobians. So the section on transformation. So it's primarily going to be an exam on multiple integrals, double integrals, triple integrals, changing, to different viewpoints, cylindrical, spherical, polar, or something else if we deem it appropriate. So we'll talk more about that on Wednesday as well, like what specifically to expect on the exam. So with that, any last questions before I stop our recording?
I have a quick question for you. Have you ever heard of a thing called a black brain?
Never heard of that
BRANE?
word. Nope.
Okay, so I just stumbled upon this this morning. I was listening to a physicist talk about dimensions.
Okay.
And apparently I don't know much about it, but apparently there's these things called black brains. They're similar to black holes, but instead of being a singularity inside, there's a surface, a dimension inside.
Okay.
And I
So
was just curious if you've ever heard
like a
about it.
black membrane. hence the-
Exactly. That's where it comes from.
Never heard of them. I have no idea about them, so I'm not gonna try to bullshit you about it.
Okay.
But I'm intrigued for sure.
Well, I just stumbled upon this morning, so I'm gonna go down the rabbit hole after physics.
All right. So I guess we'll have a conversation about this in a future point once we get a little more read up on it.
Yeah.
Okay. That works for me. All right. Anything else? All right. Well, then, as always, have an awesome couple days. I'll see everybody on Wednesday. And don't forget to submit your ballots. If you haven't turned them in yet, get out there and vote. All right. See you guys on Wednesday.
See ya.
See ya.